Hi, are you ready for some more real analysis fun? Oh yeah, bring it on, Dad. Come on, bring it on. Okay, let's do it. Let's let f of x equal 1 over x plus 1 over x plus 1 over x plus 1 over x plus dot 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 forever. And we want x to be greater than 0. Okay, we're going to want to define a sequence in order to do this. So let's let a sub k equal 1 over x plus 1 over x plus dot 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 plus 1 over x, where there are k of these x's. We'll call that a sub k. Then it's pretty clear that a sub k plus 1 is simply 1 over x plus a sub k. Okay, well, we're going to have two different cases here depending on if k is odd or even. They're going to act differently. Okay, case number 1. Let's let k be odd. Excuse me. So we can let k equals 2n minus 1 for some natural n. And, of course, what we want to do, we want to show the convergence of the sequence of a sub k, where k is odd. All right, let's do that. We're going to use induction, our old friend induction. So let's look at our base case. Well, we want the indices to be odd. Well, what is a1? a1 is simply just 1x. We'll have 1 over x. And to continue with that, we want to know what a3 is. Well, that's going to be 1 over x plus 1 over x plus 1 over x. So we have 3 x's here. Well, of course, x is greater than 0, so this glob right here is going to be greater than 0. So that means a3 is simply going to be less than 1 over x, which is a1. So far we have shown that a3 is less than a1. That is our base case. Okay, now let's move to the inductive hypothesis. Let's let a m plus 2 be less than a sub m for some odd m greater than or equal to 1. Remember, we only want to look at the odd indices. So we had to drop down by 2 here, from m plus 2 to m. Okay, well, we know that a m plus 4 equals 1 over x plus a m plus 3 from this relation here. Using that relation again on a m plus 3, this will equal 1 over x plus 1 over x plus a m plus 2. Now we got m plus 2 is odd and m plus 4 is odd. Now we can continue now. We have both odds. Well, starting with our assumption right here, am plus 2 is less than am. If we add x to both sides, we have x plus am plus 2 is less than x plus am. Taking reciprocals, we have 1 over x plus am plus 2 is greater than 1 over x plus am. Okay, now we add another x to each side, so x plus 1 over x plus am plus 2 is greater than x plus 1 over x plus am. Okay, now we're going to take another reciprocal. When we do that, we get to am plus 4, which equals 1 over this last one, x plus 1 over x plus am plus 2. And so when we take reciprocals here, this will change it to less than 1 over x plus 1 over x plus am, which is the same as am plus 2. So we started with the assumption that am plus 2 is less than am, and we wound up with am plus 4 is less than am plus 2. So by induction, the sequence am is decreasing when m is odd. All right, well, let's continue. Now, clearly, any a sub m is going to be greater than 0 because all these x's are greater than 0. So this whole thing is always going to be positive, no matter k is odd or even. Okay, then by the MCT, which is the monotone convergence theorem, that's our main tool in these types of problems, the sequence am converges when m is odd, because we have shown decreasing sequence, and we have shown it's bounded by below. So now we can write using, we can write the limit as m approaches infinity of am plus 2 must equal the limit as m approaches infinity of 1 over x plus 1 over x plus am. Remember, this is just the definition of am plus 2 right here. So we take the limits on both sides. Well, here on the right, this is a continuous function for all a's, a sub m's, because we know they're greater than 0, so we don't have to worry about zeros in denominators and such. So we can take that limit on the inside. This equals 1 over x plus 1 over x plus the limit as m approaches infinity of a sub m. Okay, then we can finally write a, which we're going to call this limit here, must equal 1 over x plus 1 over x plus alpha. I'm sorry, did I say a here? I meant alpha equals 1 over x plus 1 over x plus alpha for some alpha. Alpha is the limit of our a sub m's. All right, now we couldn't do that before until we had shown that the sequence a sub m converges. So then we know it has a limit, and we're going to call that limit alpha, is all I'm saying. Okay, now we have to solve for alpha here. Okay, let's bring this big denominator up to the left. So we have alpha times the quantity x plus 1 over x plus alpha equals 1. And then we're going to get this x plus alpha out of the denominator. So we could say alpha times x plus alpha plus 1 equals x plus alpha on the right. Okay. Let's multiply all that out, and we get x alpha squared plus x squared alpha minus x equals 0. And we can divide by x now because we know that x is greater than 0. Well, this implies alpha squared plus x alpha minus 1 equals 0. Solving for alpha, of course, with our quadratic formula, alpha equals minus x plus square root of x squared plus 4 over 2. Notice we didn't use the minus square root because we know that alpha has to be greater than 0, and that requires us to use the plus sign here. So, what we have shown so far is that when m is odd, our a sub m's, our sequence of a sub m's, converges to alpha, minus x plus the square root of x squared plus 4, all over 2. All right, now let's continue to case 2, where we're going to let k be even. So we can say that k equals 2n for some natural n. And again, we want to show the convergence of the sequence of a sub k's when k is even. And we'll use induction again. In our base case, well, a2 is equal to 1 over x plus 1 over x, 2 x's. And a4 equals 1 over x plus 1 over x plus 1 over x plus 1 over x, 4 x's. Okay. Well, it's clear that x plus 1 over x plus 1 over x is greater than x because this part here is a positive quantity. All right, taking reciprocals, we get 1 over x plus 1 over x plus 1 over x must be less than 1 over x. Adding an x on each side brings us to x plus 1 over x plus 1 over x plus 1 over x must be less than x plus 1 over x. Now this implies a4, which simply is the reciprocal of this one that we just did. 1 over x plus 1 over x plus 1 over x plus 1 over x must be greater than the reciprocal of this side, 1 over x plus 1 over x, which is, of course, a2. Therefore, we have shown that a4 is greater than a2. That is our base case. All right, now let's go to the inductive hypothesis, my friends. Okay, in that regard, let's let am plus 2 be greater than am for some even m greater than or equal to 2. Now we want everything to be even in this case. All right, we know that am plus 4 equals 1 over x plus am plus 3, which equals 1 over x plus 1 over x plus am plus 2. So the m plus 2 is even and the m plus 4 is even now, since m is even. Okay. Well, starting with our assumption here, we add x to both sides. We can say x plus am plus 2 is greater than x plus am. Taking reciprocals, 1 over x plus am plus 2 is less than 1 over x plus am. Adding x to both sides, x plus 1 over x plus am plus 2 is less than x plus 1 over x plus am. Well, now this implies that am plus 4 will equal simply the reciprocal of this on the left up here, 1 over x plus 1 over x plus am plus 2. So we just took the reciprocal here, so we got to take the reciprocal here, which will change the inequality, which means that is greater than 1 over x plus 1 over x plus am, which of course is am plus 2. So we started with the assumption am plus 2 is greater than am, and we wound up am plus 4 is greater than am plus 2. Therefore, by induction, our sequence of am when a is even is increasing. And of course, it's very clear that looking up here at our original definition of AK, this big blob right there, that's always a positive thing. So no matter what k is, AK is going to be actually less than or equal to 1 over x. In the case k equals 1, it'll equal 1 over x, I suppose. But we're doing m even, so that really won't apply here. So clearly we can say a sub m, and m is even, is actually just strictly less than 1 over x. In any case, it doesn't matter. We've found an upper bound to our a sub m's. Therefore, again, by the MCT, the monotone convergence theorem, this tells us that our sequence am for m even converges. So now we're able to write the limit as m approaches infinity of am plus 2 equals the limit as m approaches infinity of 1 over x plus 1 over x plus a sub m. And again, we have a continuous function of the a sub m's on this side, so we can bring that limit on the inside. So this equals 1 over x plus 1 over x plus the limit as m approaches infinity of a sub m. And we're going to call the limit as m approaches infinity of our a sub m, m even, we're going to call that beta. So we can say that beta, that's the limit on this side, equals 1 over x plus 1 over x plus our beta again. Well, you'll notice this is the same equation as we had in case 1. Where it's at, same equation there, except a beta instead of alpha. We solve for beta, and we'll get the same answer, of course. So beta will equal alpha, which equals then, if you will recall, minus x plus the square root of x squared plus 4 all over 2. Very good. So we have shown now that the sequence of A odd is convergent and it equals this quantity. And we have also shown that the sequence of A evens also converges and also equals this same quantity. So let's let capital L equal alpha equal beta. All right, let's bring this baby home. Now, what we want to do now is to combine these two sequences, our A sub odds and A sub evens, into one sequence. So we're going to let C sub 2n minus 1 equal A 2n minus 1, and C 2n equals A 2n. And we're going to set our sequence C sub j will equal the union of these two, our sequence of A sub 2n minus 1 and our sequence of A sub 2n's. And what we want to show, of course, is that the limit as j goes to infinity of our C sub j's equals our capital L, the same limit as each one of these sequences is individually. So we're going to order C sub j will equal simply A1, A2, A3, A4. So it's basically just our original sequence of A sub k's. I'm not quite sure why I renamed it, but I did it, so we're going to go with that. All right, let's go to the proof. By way of contradiction, let's suppose that our C sub j does not approach L. Okay, well, what we know so far, though, from before, that since A sub 2n minus 1 approaches L and A sub 2n approaches L, we can say that for epsilon greater than 0, there exists a capital N sub 1 greater than 0 such that the absolute value of L minus A sub 2n minus 1 is less than epsilon for all small n greater than capital N1. Simply the definition of convergence of a limit. And also, we can also say there exists a capital N2 greater than 0 such that the absolute value of L minus A sub 2n is less than epsilon for all n greater than capital N sub 2. Okay, now let's let capital N equal the max of N1 and N2. Then we can say that the absolute of L minus A 2n minus 1 is less than epsilon, and the absolute of L minus A 2n is less than epsilon for all little n greater than capital N. Very good. Now, since we assumed Cj does not approach L, we can say that for any capital N greater than 0, there must exist a j greater than n such that absolute of L minus C sub j is greater than or equal to epsilon. Okay, let's take this in two cases again. Case 1, suppose this little j that makes this so is odd. So we can let j equal 2n minus 1 for some little n. And then we know by our definition of our c sub j's that c sub j must equal a sub 2n minus 1. But the absolute of L minus C sub j will then equal the absolute of L minus A sub 2n minus 1, which we know is less than epsilon by the convergence, again, of A sub 2n minus 1s. And this is true for all little n greater than capital N. But in particular, since n is greater than capital N, 2 times little n minus 1 must also be greater than capital N, which implies, from our assumption here, that Cj does not approach L. This implies the absolute of L minus Cj must be greater than or equal to epsilon. And therefore, we have it absolute L minus Cj is less than epsilon here, and we also have it as greater than or equal to epsilon, so we get a contradiction. Therefore, case 1 cannot happen. Okay, very similarly, case 2, suppose this j we found is even. So we can let j equals 2n for some n. Then our c sub j equals a sub 2n by our definition of our c sub j's. But the absolute value of L minus Cj then will equal the absolute value of L minus a sub 2n, which we know is less than epsilon for every n greater than capital N. But in particular, it is true for 2n greater than or capital N, which implies the absolute of L minus Cj is greater than or equal to epsilon by our assumption that Cj does not approach L. Okay, again, we get a contradiction. We have it less than epsilon, and we have it greater than or equal to epsilon. So therefore, case 2 cannot happen either. Therefore, by way of contradiction, Cj must, in fact, approach capital L. Therefore, we finally can say that f of x equals L, which equals minus x plus the square root of x squared plus 4 all over 2. And if you like this video, maybe think about giving it a like. And thank you very much for watching.